Hey guys, today we're going to talk about the laws of electromagnetic induction. So, what is electromagnetic induction? It occurs whenever the magnetic field through a conductor changes. It can be due to a conductor moving through a magnetic field or a conductor being in a fixed position with changing magnetic fields due to AC circuits. So, both of these scenarios induce EMF. So defining magnetic flux and Weber. So the magnetic flux is defined as the number of magnetic field lines passing through a given surface area. And the Weber is the unit for magnetic flux, and 1 Weber is equal to 1 Tesla meter square. Factors affecting the magnitude of induced EMF. So induced EMF depends upon the flux density, the length of the conductor, the velocity of the conductor, the angle between the velocity direction and the flux direction. So now, taking a deeper look into the magnetic flux. Magnetic flux, as I said earlier, is the number of magnetic field lines passing through a certain area. So if you see in the slide here, the magnetic field lines are parallel to the surface area, which means the angle between the magnetic field lines and the surface area is 0. When you substitute 0 as the angle over here in this equation, you will get BA cos 0 degrees, and cos 0 is 1. Hence the equation will become magnetic flux is equals to magnetic field lines into area. So this formula gives the maximum flux in any situation. As you can see in the second diagram, the magnetic field lines are perpendicular to the area, which means the magnetic field lines are 90 degrees to the area. So when you substitute 90 into this equation here, you will get BA cos 90, and cos 90 is equals to 0, and any number multiplied into 0, you will get 0. So the magnetic flux in this diagram will become 0, giving the minimum flux in any situation. So whenever there is a perpendicularly illustrated magnetic field in area given to you, it is giving the minimum flux of 0. And in the third diagram here, the surface area is slightly slanted and the magnetic field lines are going this way. So the A here stands for the area, the direction of the area, and this way is the magnetic field. So the angle between it is anywhere between 0 degree to 90 degree, which is a valid number, giving a magnetic flux of something between minimum and the maximum flux. So you have to use the formula BA cos theta because it has some angle here. But for this case, you do not need to use the cos theta here because it's just cos theta is equals to 1. So you just have to use BA. So when the magnetic field lines are parallel to the surface area, you just have to use magnetic flux is equals to B into A. In this case, you have to use the whole equation. Magnetic flux is equals to B into A into cos theta because there is some value of theta here. Next, we have magnetic flux linkage. So magnetic flux linkage and magnetic flux doesn't have much difference in between them because magnetic flux, I have given a small diagram here which actually gives a clear illustration of what is magnetic flux and what is magnetic flux linkage. So if you see carefully here, there is only one circle here, which means you can take it as the representation of one loop or one coil. Okay, so magnetic flux simply means one loop and magnetic flux linkage means many loops. That's all, that's the difference. So when a magnetic field line passes inside a loop created by a conductor, it is said to be linked by that conductor. If the conductor is made out of multiple loops, for example a solenoid, then this magnetic field will be linked by each loop in the solenoid. So this means that for a solenoid, the magnetic flux linkage is the magnetic flux passing through the cross-sectional area of the coil over here multiplied by the number of turns. So this is the formula for magnetic flux linkage. The number of coils into magnetic flux, and magnetic flux is equals to magnetic field into area. Now, looking at Faraday's law and Lenz's law. So when there is a change in magnetic flux, it generates EMF to run current around it. As we recall earlier, magnetic flux is magnetic field times area. We already know that when we have current, it generates magnetic field around it. The way this law works is that systems do not like change. So whenever the magnetic flux changes, the current is induced in such a direction as to minimize that change. So the important formula for this law is given over here. The EMF is represented by this E, which is equals to minus of the change in magnetic flux divided by the change in time. Okay, so the minus sign here is Lenz's law. Lenz said that the electromotive force will oppose the change in magnetic flux. So in this part here, in this part of the slide, you can see an example I've given you on how the magnetic flux changes the current induced in such a direction as to minimize the change. So I will explain to you how the change is occurring here. So in this first part here, when you insert a magnetic bar, okay, a bar magnet inside the solenoid here, this part, which is the north pole of the magnet, when it's inserted in the solenoid, this part of the solenoid becomes north pole, repelling the magnet away from it. Okay, so the induced field inside the coil will be this direction. And if you look at this part here, this is when you're pulling a bar magnet out of the solenoid. So when this is the north pole, this part of the solenoid becomes south pole and does not let the bar magnet go. So this is repulsion happening here, and this is attraction happening here. It does not let go of the bar magnet, and the induced field inside the coil is this way. Hence the current is this way. So with that equation given, let's solve a question here. A 5 Tesla magnetic field directed out of the paper changes to 0 Tesla in 0.1 seconds. Determine the EMF generated in a wire loop 2 meters square in area and the average current if the resistance is 20 ohms. So you have to importantly take down all the values given. That's the first step you should do before solving any question. 5 Tesla of magnetic field changes to 0 Tesla in 0.1 seconds, and the wire loop has an area of 2 meters square, and you have to find the average current and the EMF generated, and they've given you resistance of 20 ohms. So before I continue with the video, I want whoever's watching the video to try and pause the video and try this question before continuing it. Okay, so now we will use the formula I've given here. The EMF is equals to minus the change in magnetic flux divided by the change in time. If you substitute, so according to the question, they have not given us magnetic flux. But they have given us magnetic field and the area. So the so you have to find the change in magnetic flux. If you want the change in magnetic flux, it should either be a change in area or the change in magnetic field. Since the area is fixed here, 2 meters square, we're going to look for the change in magnetic flux, the change in magnetic field. So here you have 5 Tesla as the initial magnetic field and 0 Tesla as the final magnetic field. So the change in magnetic field into area, you will get minus 5 Tesla into 2 meters square. So the magnetic flux of this case here will be minus 10 Tesla meter square. So to find the EMF, you're going to just substitute the values you've gotten, whatever values you have, into this formula here, minus of the change in magnetic flux divided by the change in time. So change in magnetic flux, you have to remember to put the negative sign in front of the change in magnetic flux, because the negative sign states Lenz's law. So minus bracket minus of minus 10 Tesla divided by 0.1, which is the time taken, will give you 100 volts. I have written volts here because EMF gives volts, or otherwise you can just use the formula, this formula to give you the units. And now to find the average current, you have to do volt divided by R, as all of you already know, I is equals to V by R. So the volts you have found here, 100 volts, and the resistance is already given in the question, 20 ohm. So 100 divided by 20, you get 5 amperes. That's all. Now we're going to look at simple applications of electromagnetic induction. So you have metal detectors, braking systems on train, AC generators, card readers, microphones. So now we're going to talk about a magnetic strip card. So a magnetic strip card is a type of card capable of storing data by modifying the magnetism of tiny iron-based magnetic particles on a band of magnetic material on the card. So as you can see here, this is the magnetic strip. So the magnetic strip, sometimes called as the swipe card or mag stripe, is read by swiping past a magnetic reading head. So that's all for today's class, and thank you all for watching the video. Please remember to subscribe and comment your favorite topics that you want us to be uploaded, and remember to like, subscribe and push the bell button.